What you see is a diagrammatic representation of a Van de Graff generator. What is it, and what does it teach us about electric fields? Let's find out. A Van de Graff generator is an electrostatic generator which uses a moving belt to accumulate electric charge on a hollow metal globe, referred to as the dome, creating very high electric potentials. When it is turned on, the dome becomes charged. It can either be positive or negative depending on its design. If something comes in contact with a dome, it also gains the same charge as what is on the dome. So in a situation where a person holds the dome, they become charged and their hair will stand on end. We know light charges repel. The force of repulsion between the charges on the person's head and hairs is strong enough to make the hair stand up. The charges on the hair are clearly experiencing a force. If electric charges feel a force, then they are said to be in an electric field. Therefore, there is an electric field around the Van de Graff generator or the dome and the person touching it. What then is an electric field? The region of space where an electric charge experiences a force due to other charges is called an electric field. When an electric charge is placed near to another electric charge, it experiences a force. It can either be attraction or repulsion. The electric force doesn't require contact between the two charges, so it is called an action at a distance force. It acts through space. If the electric force felt by the charge is the same everywhere in a region, the field is referred to as uniform, and so refer to it as a uniform electric field. Like magnetic fields, electric fields are also represented with lines having arrows on them. The arrows indicate the direction of the field. The direction of an electric field is the direction of the force on a small positive charge placed in the field. A positive charge will move away from another positive charge, but move towards a negative charge. Electric field lines therefore point away from a positive charge and towards a negative charge. The greater the number of lines at a point indicates a stronger field. A uniform electric field can be produced using two oppositely charged parallel metal plates. It is represented by evenly spaced parallel lines drawn perpendicular to the metal surfaces. The strength of the field decreases with increasing distance. As the distance of separation between the two charges increases, the strength of the field decreases. For two similar charges, either two positive charges or two negative charges, they repel themselves. The field lines therefore will never intersect as shown in the diagram. The capital E with an arrow on it stands for the electric field, and it shows that it has direction. In the case of a dipole or two oppositely charged particles, there is attraction. The fields of the two charges combine to form one field. The electric field lines point away from the positive charge and towards the negative charge. Let's consider conductors and electric fields. Charges on conductors of any shape always lie on the outer surface in static situations. That is, when charges are not flowing. When a conductor is irregularly shaped, the charges are still on the outside, but now they are not uniformly spread over the surface. The charges are most concentrated near the sharpest curve or the pointed end. This is where the electric field is strongest and the field lines are closest together. An application of this, for instance, is why a fork, when put into a microwave oven, produces sparks. The microwave will cause the fork or the metal electrons to move. The fork has pointed edges, and so charges build up at the pointed edges, producing a concentrated electric field at the sharp end, which causes sparks to be produced. To recap, test your understanding. State what is meant by 1. An electric field. You can go ahead and pause the video. From what we discussed, it is a region where a force acts on a charge. The second one, state what is meant by the direction of an electric field at a point. The answer, it is the direction of the force acting on a positive charge. And the last question, draw the pattern of the electric field in the region around the positively charged sphere shown below. Show the direction of the field with arrows. From our discussion, we've seen that electric field lines will always point away from a positive charge. And so from the depiction, we see the lines pointing away from the positive charge. If it was a negative charge, the lines would have pointed towards it. Thank you very much for watching this video. I hope you enjoyed it. Please don't forget to subscribe, comment, leave a like. I'll see you in the next one.